Okay. Well, thanks for persevering through those technical difficulties. Yeah, my name is Ben. Before we get started, I'd just like to acknowledge the traditional custodians of the land in which we're meeting on today, the Gadigal and Bidjigal people. I'd like to pay my respect to elders past and present, and any Aboriginal or Torres Strait Islanders that might be here with us today or online joining in the meeting. They're the original scientists of this land, and it's important to pay our respects to that. So what I'm going to be talking about today is SHAP values, or Shapley additive explanation values, and how they can be used to gain interpretation from these black box machine learning algorithms. So before we dive into SHAP values, thank you. Okay, before we dive into SHAP values, we're going to talk about machine learning first. This is a buzzword that you hear quite a lot, but what does it actually mean? Okay, gets thrown around quite a lot. So machine learning is defined as any computer algorithm that can draw inference by learning and updating based on patterns in your data. Okay, we'd see machine learning as a subclass of artificial intelligence. So something that might be artificial intelligence but isn't necessarily machine learning could be the early chess algorithms. There were these chess algorithms that were developed that could beat these grandmasters in chess, and they were all just hard-coded rules. If the chess pieces were in a certain position, then you do this move, okay? It wasn't train, learn, and updated based on data. It was all hard-coded in. And then we have deep learning algorithms, which are a subset, again, of machine learning algorithms, which also are trained and learnt based on patterns in data, but we are getting into more complex machine learning algorithms where you have, say, some hidden layers. There's lots and lots of parameters going on. There's, multiple layers of structure going on in there, and that's where we would classify our machine learning algorithm as deep learning. But yeah, very much all these buzzwords. So as I'm going through these slides today, I'm going to be putting up a bunch of Python code. So Python is the programming language of choice for most data science and machine learning algorithms. You can fit machine learning algorithms in plenty of other different programming software, R as well especially. But there's some nice software, and a lot of developments, especially in the deep learning end of stuff, is in Python. And there's a great package for getting out your SHAP values in Python called the SHAP package, and that's why we're going to stay in the realm of Python today. A popular machine learning library or package is the scikit-learn package. This is a classic diagram of some different machine learning algorithms that it has, and it recommends you use depending on the type of data you have and the object of your machine learning algorithm. So generally when we're doing machine learning, we're trying to do some sort of prediction, and that depends on, that prediction could be a classification problem where we're trying to understand the category of some outcome, or it could be a regression problem a regression prediction if we have some continuous outcome that we're trying to predict. We could also be doing clustering or dimension reduction as well. And depending on the magnitude and the type of data, it recommends these different things for you to do. So we're going to start off with a very simple machine learning algorithm is the linear model. This might be something that's more familiar to everyone. A linear model is a computer algorithm that is updated and trained on data. So it is classed as a machine learning algorithm. Any stats model pretty much that is trained on data is a machine learning model, okay? And we can express a linear regression model can be expressed mathematically as our fitted values y hat here is a function of x. F of x is equal to our linear intercept, our beta naught there, plus our regression slopes multiplied by each of our predictors, or as we call them in machine learning, in the world of machine learning, features. So we have these j features, we're multiplying our regression coefficients, beta 1 up to beta j, by these features, and this is how we generate our linear model function. We also have residuals in this function, the difference between our observed y's and our fitted y's, which we assume is Gaussian distributed with mean 0 and some constant variance sigma squared. So let's start off with let's have a toy data set here. We've got a Californian census data set. We're going to apply some machine learning algorithms to this data set. This is a data set that's been used in the past. So we have, from this data set, we've got 20,640 blocks of houses. So multiple houses within a block. And our goal is to predict the median house price measured in hundreds of thousands of US dollars within a block. Okay. So we've got 20,000 blocks of houses, and we have a whole bunch of information on the following variables. So we have the median household income of people within a block in tens of thousands of US dollars, the median house age, the average number of rooms per household, average number of bedrooms, the total population of people living in the block, the average number of household members in the block, and some spatial coordinates of the block itself, latitude and longitude. So we can fit a linear model in Python. We can extract out our regression, our parameters, and our 95% confidence intervals for these parameters. So we have here in the first row is our linear intercept, which isn't that important to us. And then we have our regression slopes and some 95% confidence interval for those slopes. So if I wanted to get some interpretation from this machine learning algorithm, I could look at the regression slopes. Okay, so I could look at the regression slope for median household income. It's 0.4256. So median household income is measured in tens of thousands of dollars. Median house price measured in hundreds of thousands of dollars. So we would interpret this regression slope as saying, as median household income increased by $10,000, we predicted the median house price to increase on average by $42,560 with a 95% confidence interval from 38,940 to 46,190. So this is great. We are getting some understanding of both the direction of the relationship between our predictor or our feature household income, median household income, and our predicted response, as well as the magnitude of that effect as well, with some confidence around that estimate. What if we wanted to ask, say, what is the relative influence on these parameters on our outcome? Okay, so we have 8 different features here. I want to know which of these features is most important at predicting our outcome. What's really driving our predictions? We can't just rely on the regression slope itself in this example here, because that is relative to the scale of the parameter. For example, if median household income wasn't measured in tens of thousands of dollars, if it was measured in hundreds of thousands of dollars, then this regression slope is going to be 10 times as big. It's going to be 4.256. So it's relative to the scale of the feature. So, okay, well, we could handle that. Let's just scale all the features, and they're all in the same scale. And now we have parameter estimates that are relative to each other. Yes, that is something you could do, and then you could get out your relative influence of these features. You could also do variance partitioning. We could understand the amount of variance that is explained by each of these predictors or these features by looking at the change in R squared from adding and removing them from the model. But what about when we get into more complicated settings? Okay, what happens when we get into these deep learning models? They've got lots and lots of parameters. This is a diagrammatical representation of a multi-layer neural network. We have some hidden layers. You could have hundreds, thousands, millions of parameters in some of these models, or billions even in the large language models now. And each parameter in these models can be related to all the features or multiple features. Okay, before we had regression slopes parameters that were related to individual features. We had an additive model. We didn't have interactions going on. Now we're getting into a bit more of a complicated setting, and we need to have something fit for purpose here. Okay. So this is where SHAP values really come in handy. So SHAP values, or Shapley additive explanation values, What they try and do is find the contribution to a model's prediction by averaging its contribution across all possible subsets of features. And we have this scary looking equation here in front of us. And what I just said might sound like mumbo jumbo as well. But that's okay. We're going to go straight into an example to try and break down what that means. Okay. So the idea comes from game theory, right? The idea comes from game theory where we're trying to find the payout of adding players to a game. Okay, so let's say we have 3 players. We have player A, player B, and player C. And we're trying to find the payout of adding A to the game. The average payout of adding A to the game, we're trying to find the SHAP value for A, okay, for this particular game. So there's a lot of different ways that these players can join the game. Okay, well, there's six different ways. First, A can join the game, then B can join, then C can join. Okay, or A can join, then C can join, and then B can join, and so on and so forth. What we're mostly interested in is A's contribution to the game. And there's actually, although there's 6 different combinations of how the game can be formed, there's only 4 combinations, unique combinations of how A gets added into the game. So in these first 2 combinations here, A is added into an empty game. There's no one else in the game. A is the first one in. And we call this our first coalition block. The second coalition block, A gets added in after B. And then A gets added in after C, and then A gets added in after B and C. So there's 4 different scenarios in which A can get added in, and there's sometimes multiple combinations within a coalition. And what we're trying to work out is we work out the coalition's value after A is added, and we subtract from this the coalition's value before A is added to get A's contribution to this coalition. And then this scary looking fraction here, that is just appropriately weighting our sum by the fact that there is multiple combinations in some of these coalitions, whilst other coalitions only have a single combination in it. Okay, but that's the basic idea of what we're trying to do. And we can extend this idea to a machine learning context where we can find the value of having a predictor in our model by basically using conditional expectations and averaging out the effects of other features in our model using a background random sample of our data set. And we will go into that with a direct example as well. This is a little bit to wrap your head around what's actually going on here. So let's look some code. So we're going to import some libraries here in Python. We're going to import the SHAP library, the sklearn library or package, whatever you call it. We're going to import this pyplot from matplotlib and call it plot, and this sm from statsmodels.api, which is just to add in a constant to our data set. So first we're going to load our data set just so everything runs a bit quicker. Instead of using all 20,000 housing blocks, I'm just going to use the first 1,000. And then I'm going to add a constant intercept column to our predictor or feature matrix X. Okay. And then I am going to, oh, we actually don't need that. You notice errors. Yeah, we never end up using this. Okay, and then we fit a simple linear model using sklearn. So we load the linear model, linear regression from sklearn. We fit this model to our data. Our X's and our Y's are added into this model. Okay, then what we do is we calculate our SHAP values. Okay, and we calculate that in 3 steps. The first step is to get some background samples. Okay, so we're going to take 100 random samples from our feature matrix, and we use this, SHAP uses this to help calculate the SHAP values. You can take more if you want. You'll get more accurate SHAP values. But it will take longer to run, basically. Okay, so you can play around with that if it's changing the number of background instances you need, whether it affects your SHAP values that you get out. Then what we do is we create an explainer function where we feed in these background samples and the predictions from our model. And then we feed our feature matrix to that explainer function, and that's how we get our SHAP values. So let's talk about what these SHAP values actually are in a linear regression setting. So what I've got up here is a partial dependence plot. Those who've seen partial dependence plots, it looks familiar. If you haven't seen a partial dependence plot, what it is, on the x-axis, we have our median household income. It's one of our predictors. And on the y-axis, in this blue line here, we are plotting the expected value of our function given the median household income is equal to a certain value. So if we averaged out everything else in the model and the only thing we change is median household income, then this is the line that we get. Okay, and we can see we've got some dotted lines in here as well. So the vertical dotted line here is the expectation of the median household income. This would the average median household income, and the expected value of our function. So that's the average prediction that we get from our function. What the SHAP value is for a linear model is simply the difference between our partial dependence line here, the conditional expectation of our function, given our feature is equal to some value, minus the average predicted output, the expectation of the function itself. Okay, so that's what this red line represents here. And we do this for every sample in our data set. So each block of houses, we calculate this, this SHAP value. Okay, and we can plot these SHAP values, and you can see it's now just a mean-centered partial dependence line. It looks very similar in this setting. Now, this isn't the case for all machine learning algorithms. It's not always this simple. Calculating SHAP values is actually quite complicated as you get into more complicated machine learning algorithms. It's only in this setting with linear regression models that we have this nice relationship that we can see with a partial dependence plot. And the reason we have that is because a linear regression model is additive. We don't have interactions in our model. As soon as we start to have interactions going on in our model, we don't have this nice relationship. And we'll see that later on. Okay, so let's try and understand how to interpret our SHAP value. So it's okay if you don't fully understand how SHAP values are generated. The important thing that I want to get you to get out of this lecture or seminar is to understand how they can be useful and how to interpret them. Okay, but I thought it was useful to try and give a brief introduction in how they're generated anyway. So what we've got here is what's called a waterfall plot. So this is for one sample in our data set. So this is for one block of houses. And the way that you read this is from bottom to top. Okay, so at the bottom, we start out at our expected value of f of x, which is our average predicted value. So on average, we're predicting 1.904. So the average median house price that we predict is $190,000 US. Okay. And this dotted line up here is where we end up for this particular block of houses. So this particular block of houses, they're worth quite a lot of money. They're worth $330,000 $339,000 or 339,000 US dollars. The median house price of houses within that block. So what SHAP values tell you is how for this particular sample, how we've gone from the average predicted value to the observed predicted value for that particular sample. And we're trying to divvy up how the features are contributing to that difference. Okay, so the average number of rooms in houses in this particular block is 5.4. Okay, and that increases our prediction by 0.02. The average number of occupants is 2.81. That's positive. That's going to increase our predicted house price by 0.03. The total number of people in the block is 385. That reduces our prediction. The house age increases it. Average number of bedrooms decreases it. And now we get into the factors that are really driving what's going on for this particular sample. The longitude decreases our prediction, the latitude increases it, and median household income, $64,000 as a median household income, it's pretty high. That's increased our prediction quite a lot to make us end up at this very high predicted value of 339,000 US dollars as the median house price. So we can look at this for different blocks, different samples. So we're going to have another look at another block of houses. And what do we notice? We notice that the starting point is the same, 1.904, because that's the average predicted value. That's going to be the same across all our samples. But where we end up now is different. Now we have a block of houses that are worth less than the average. Okay. And again, we can see how we sort of get to that. It seems that median household income and these spatial terms are mostly driving that change. And again, have another waterfall plot. Our starting place is the same. Where we end up is different. And it seems these three parameters are really what's driving that prediction. Okay, but that's well and good, but that's only for 3 blocks of houses. In my sample, I've got 1,000 blocks of houses, or in the entire data set, there's 20,000 blocks of houses. I want to know what the relationships are in general, okay, to extend this outside of just a couple of examples in our data set. So what we can do is we can plot what's called a B-swarm plot. So we're plotting here all of our SHAP values for every single sample in our data set. And we're going to color the SHAP values based on the feature values. Okay, so let's try and have a look at that. So for higher feature values, it's red. For lower feature values, it's blue. So let's look at latitude up the top. We can see for larger values of latitude, these red values here. So as latitude increases, our SHAP values decrease. We imply then that latitude is negatively related to median house price. Okay, as latitude increases, the SHAP values decrease, the median house price decreases. Okay, same for longitude, sorry. Whilst median household income, as you might expect, is positively related to median house price. Okay, for larger values of median household income, we get large positive SHAP values, meaning it is positively related to the outcome. So having a look at this B-swarm plot gives us an understanding of both the magnitude of the impact these features have on the model, as well as the direction of the effect. Okay, so you can see here the population of a block size doesn't really matter that much. It's arbitrary. It's like the size of the block, right? It doesn't seem to impact that much to our model predictions. If we wanted to as well, we could try and, another thing to point out as well is there's these nice linear relationships. It nicely goes from red to blue, okay? There's no blue points over where the red points are. That's because we're fitting a linear regression model, right? We're fitting linear relationships, so we're observing these linear relationships in the bee swarm plot. That doesn't necessarily happen when we get into more complicated models. So if we wanted to have a look at variable importance, we can take the absolute value of all of these SHAP values, so just looking at their influence on the prediction, okay? And then we can take the average of these absolute values of our SHAP values, and that can give us an understanding of what is driving our predictions in this model. And it seems that latitude, as we've seen with our examples, it's these spatial terms, the most important: latitude, longitude, and then median household income, okay? So this is all well and good, but we could already understand a linear regression model, right? We could do that at the start. So the whole point of using these SHAP values is to understand more complicated machine learning algorithms. So let's do it. Let's apply it to a more complicated algorithm. So we're going to do a tree-based gradient boosting algorithm, XGBoost, a famous gradient boosting algorithm. We're going to import the XGBoost package in Python, and then we're going to run it. We've got an XGB regressor because we have a continuous outcome. We're going to have 100 estimators, a max depth of 2. We're going to fit this function. I'm not going to go into the details of what an XGBoost model is, but this model can have up to 1,000 parameters, and we have interactions in it. It's no longer an additive model, okay? Again, we can get out our SHAP values in the same way. We don't have to get we've already got our background distribution, our random samples. We can load that in here again. We put in our model and to form our explainer function, and then we feed our feature matrix X into this explainer function. And we can have a look at what the SHAP values look like now. So I've plotted here the SHAP values for median household income. And you can see it looks a little bit different to what we saw before in the linear model. If we look at the linear model one, when we plotted our SHAP values, firstly, it's linear. We're no longer fitting a linear model anymore. We can have wiggly effects, nonlinear effects going on. But the other thing that you might notice is that for a given value of median household income does not uniquely determine what the SHAP value is. So for a given median household income, you can get multiple different SHAP values, okay? Whilst before here, for one household income, one SHAP value, right? Now we can have multiple. There's a vertical variation now. So, and we're getting that vertical differentiation because of interactions in our model. Okay, and we can have a look at some of these interactions by coloring those points based on the feature values of other features in our model. So right now I'm going to color the SHAP values by the average number of occupants in a house. And so the red points, there are more occupants in a house. The blue points, there are less number of occupants in the house. And we can see this interesting relationship, okay? For blocks of houses where the median household income is small, we can see the red points are on the top and the blue points are on the bottom. So we interpret that if you're in blocks of houses where people aren't earning that much money, those blocks of houses, the houses in those blocks tend to be worth more money if there's more people living in those houses, okay? However, the reverse is true when we get into more wealthy blocks of houses. If we're in blocks of houses where people are earning more money, we can see the blue points now on the top and the red points are on the bottom. So if you're in places where people are earning more money, the houses seem to be worth more if there's less people living in them. So it's this inverse relationship. As we change the median household income, right? So this is an example of an interaction effect that you can pull apart using SHAP values. We can also get out waterfall plots. So in the same way that we had waterfall plots in our linear regression model, we can get out waterfall plots here as well. So where we start now is slightly different because our average prediction is different, because we've got a different model. Now our average prediction is 189,000, okay? But we're still predicting a very large positive prediction for this first block of houses, and it seems that median household income is really driving that point home. The people in this block are earning quite a lot of money. We can get out our B-swarm plots again as well. Okay, it looks a bit different to what we saw for the linear regression model, and well, a couple of things, right? One thing you might notice is that we no longer have a linear trend from blue to red in here. So for example, for population, it goes from blue to red to blue again. Okay, so we're allowing non-linear trends to be fit in our model, and we can try and pull apart those non-linear trends here in the B-swarm plot too. Again, we can get out our variable importance by taking the average of the absolute value of our SHAP values. You can also produce what's called a heat map, if you like. So might be a bit confusing, but there's a lot going on in this plot, but you basically read it left to right, and it goes row-wise down your data set. Okay, so we've got 1,000 blocks of houses in our data set. So the first block would be this column here, all the way to the last block is our last column here. And it's basically like having our waterfall plots for every single sample in the data set. So this doesn't tell us anything about the direction of effects to our prediction. It's ordered based on the structure of our data. So this kind of plot might be more useful if you have, time series data or something, and then you order your data set based on time or something, and then you can see how your predictions change over time. Up the top here, we have our predicted values and how they change going down in our data set. And we also have our bar plot of our feature importance. Okay. We can also produce a violin plot, which is just a smoothed out version of the B-swarm plot that we saw earlier too. Okay, so that's great. We've talked about how we can apply SHAP values to a prediction task, looking at estimating a continuous outcome. It's not just limited to continuous outcomes. We can also use it for categorical outcomes as well. So let's have a look at another data set, another toy example. So in this example here, it's from the 1994 census, and we're trying to predict whether an individual's income is more or less than $50,000. And we have a whole bunch of feature variables that we're going to use to predict whether they're a high or a low earner. We have their age, the type of employment, their education level, marital status, occupation, relationship, race, sex, the amount of capital gains they've made, capital losses they've made, how many hours they work per week, and their country of origin. Notice we have a few categorical predictor variables in here as well. That's fine. SHAP has some nice functionality to work around categorical predictor variables too. So we're going to load this adult data set from the SHAP package. We're going to fit our XGBoost model again, except now we're going to use XGB classifier instead of XGB regressor. And we're going to use the log loss function as our loss function to train and optimize this model. And again, we're going to compute our SHAP values as we have before. for whatever reason, to get some nice plots, they like to have a display version of the data as well to use for plotting, which has our string values in it. Okay, so again, the waterfall plot, we can read it off in the same way. Okay, we have our expected predicted value. This is where we ended up for this particular individual. And we can see that what's largely driving it is their age, their occupation, and their relationship status. We have a look at a B-swarm plot, okay? And we can see with that B-swarm plot, even for categorical variables. So yeah, like I wouldn't necessarily trust the color of these. It's just to signify that they're different groups. You know, there's not necessarily a better or worse relationship status. It's not, you know, it's a category itself. But we can see the sort of 3 different categories there plotted. Same for occupation. We get these distinct colors, which are representative of different occupations, as well as sex. So a couple of interesting things going on that you might notice here. Firstly, capital gains, right? If you have no capital gains, it barely impacts the model predictions at all. But if you have capital gains, it impacts the prediction a lot, right? These red values, and we do have capital gains, they're really driving in, you know, altering our probability of whether someone is earning more or less than $50,000. So if we only wanted to look at the influence of these variables, we could take away the direction of this and just take the absolute value of them all. This is an alternative to doing the bar plots that we saw before. And this helps to drive home that point that we talked about. We've you know, a lot of the time capital gain does nothing, but when it does do something, it does quite a lot, okay? And yeah, so that's an alternative to doing this variable importance plot, where we're just looking at the average itself. You can also look at the maximum SHAP value, which would then show the capital gains being really important. There's so many different plots and things you can play around with. We can also have a look at interaction effects like we have before. So we're going to plot all our SHAP values for age. So you can see as someone gets older, they tend to earn more money. Okay, it makes sense. Although it drops off a bit when a lot of people start to retire. And we're seeing that we don't have an additive model anymore. We've got interactions going on. Just like we saw in the previous model, for a given age, you have multiple SHAP values, and that is dependent upon other terms in your model. So let's color it based on these other terms. So we're going to color it based on the amount of education that a person has. And we can see this interesting interaction effect going on. So for higher educations, if you're going to university or seeking higher educations, that's signified by red points. Less education, blue points. Okay, and we see this interesting relationship where if you're someone that is young, so like less than 30, you tend to earn more money if you're less educated. So the blue points are at the top if you're less than 30. So those are the higher earners. Whilst the reverse is true if you're older than 30. So if you're older than 30, you get the red points on the top, you tend to earn more money if you have that higher education. So this is seeing the payout of getting higher education, short-term loss, long-term gain. And we can see this with this example. We can also have a look at capital gains. So if you're of a working age, from over 20 to younger than 60 or so, having capital gains seem to increase your income. Whilst if you're not of a working age, or getting into more of this retired category, or older than 60 or less than 25, The reverse is true. Having lots of capital gains, for whatever reason, seems to imply that you're less likely to be earning more money. Maybe because you're relying on these capital gains. You don't need to be having that income. I don't really know. We can also look at this for categorical predictors on the x-axis as well. So we've got our relationship status and how the influence on our prediction depending on the number of hours per week that you work and how that changes. So if you have a husband or a wife, you tend to be earning more money. I guess that's related to you being in a later stage in life. And interestingly, for both of them, if you're working less hours per week, you seem to be earning more money. And again, that might just be related to your being older. And so you have kids and you have less hours in a week that you can work. But because you're older, you're getting paid more money anyway. You're further into your career. So we can go all the way to the other extreme of this and apply it to a really, really high parameterized model, a large language, natural language processor model. Okay, so what we're going to load a sentiment analysis model. So what this model does is it's trained to be fed a paragraph of text, and then it predicts whether that paragraph of text is a positive sentiment or a negative sentiment. Okay, and we're going to apply this to some movie reviews, some IMDb movie reviews, and we're going to try and see if this model can predict whether the movie reviews are positive or negative based solely on the words in the review, okay, and the structure of the words in the review. All right, so we've got to load a whole bunch of packages, the torch package, the transformers package. We're going to load this tokenizer, which converts our words into numbers, basically, that can be fed into the natural language processor model. We're going to load a pre-train, so it's already been trained on some training data, sentiment analysis model. All this weird code is just defining how we make these predictions based on feeding it text, paragraphs of data. We load our IMDb data set and we calculate our SHAP values with some added parameters in here that are required for when you're doing it with natural language processor models. Okay, so we can get out a waterfall plot, but for text, it's called a text plot, and it looks a little bit differently, but it can be read in the same way as our waterfall plot. So we start at our base value, we end at this value here. So the base value is our average predicted sentiment. So this particular review is more negative than the average review. And we can see what words are driving this negative review. So the word pointless, that really made that more negative. Okay, it's a very negative adjective. Then tells and interesting. Those are positive words that are making the model think maybe this is a positive review. You can see it takes the position of the words in the paragraph into account. So no here has a different SHAP value to no down here. Okay. We can look at all the SHAP values and look at the the mean average of the absolute value of the SHAP values across all our reviews. And we can see a lot of the words that are driving these predictions are these strong adjectives, which makes a lot of sense. Impressive, irritating, pointless. There's a couple of weird ones in here like und and se, but I think those are just a couple of instances of those that happen to be large. You know, this isn't taking into account the frequency of the words. If there just happen to be one word that happened to be quite large, it'll show up in this plot. So if we wanted to take in the frequency, we could have a look at the sum, just summing the SHAP values of all these words. But now this is relying a lot. This is being now driven a lot by the frequency of these things. So it comes out that full stop and comma and film and the are the most important things that are driving what's going on. All right. Thanks for sticking with me as we went through that. It's a lot to wrap your heads around. So thanks for coming with me on that journey. The materials from this presentation were largely, well, it was pretty much entirely, I just went through the SHAP module document and introduction to explainable AI with SHAP values. So if you want to have a bit more time to go over this while I'm not, talking in your ear, I'd recommend checking out that document. You could also try the textbook Interpretable Machine Learning, a guide for making black box models explainable. Thank you. Any questions? Yes. Can you do it in R? I'm actually not sure. I'm sure there would be a way.
Oh, it's just you mentioned it. I just wondered whether it wasn't an R package.
Yeah. There's just nice ways of doing it in Python, basically. Yeah. Then maybe there's a way of doing it in R. The issue is, as you get into more complicated machine learning algorithms, it becomes really hard, to calculate SHAP values. And there's better functionality to fit those models anyway in Python. Yeah, I'm actually not sure. Oh, there's an R package, SHAP R package. SHAP R. Okay, there you go. You can do this in R as well. There you go. Yeah. Any other questions? Yes, Nixon.
The only way to look at variable products, how would these SHAP values compare to some other method?
Okay, so for those online that might not have heard that, Nixon asked, SHAP values isn't the only way that you can break apart what's going on in a machine learning algorithm. There's lots of other things that you could do. How does it compare to other things that you could do? Again, not too well versed on a lot of the different methods. I've seen what some people like to do is they randomly per tube, like mix a feature and then see that as how that impacts the model predictions, right? So if you randomly shuffle one of your features and see how that impacts your prediction and how much worse it gets, then that is an understanding of how important that variable is, because you've just turned it into nonsense. So if you've turned it into nonsense, how much worse did it make your mean square error or something? And there's so many different things that you can do to get out stuff. The nice thing about that other approach is that you can just apply it to anything. It's model agnostic, but you don't get as many insights. The nice thing about SHAP values is you can get out the direction of the effects. There's a lot of great software for doing this. It can be applied to most machine learning algorithms as long as it's in the realm of being able to interact with the packages that are fitting with it. So I guess the downside of using SHAP, if you're using some machine learning algorithm that isn't in sklearn or isn't connected with the package itself, it might not be able to calculate the SHAP values and you get all these nice interpretations and stuff out. Whilst there are other methods that are fully model agnostic. Like it doesn't matter, like you can come up with your own thing entirely and you could still get out variable importance and stuff, but you don't get as much interpretation. As to whether methods give you more accurate information on variable importance, I'm not really well versed on that particular aspect. But yeah, SHAP seems to be a pretty popular thing that people are doing now. Yeah. Does anyone else have any other questions?
And there's a question in the chat.
Okay. Let's get the chat up. Okay. How do the absolute value average of the SHAPs compare, say, with the included importance values calculated, say, on random forests in R package? Random forests, are they consistent with each other? I have no idea. This would be a good thing that you could try and see if they match up, whether the importance values in the random forest package in R matches up with the importance values that you get from the SHAP package. I'm not sure, but you could try it and have a go. Yeah, sorry, I don't have more answers to that.